Naive-based classifier is a classifier that predicts the class with the largest posterior probability. So as you can see on the equation on the right-hand side, this is defined as the argument that maximizes the probability of class y sub c given the data x. So this classifier is based on the Bayes theorem, as you can imagine, which is depicted for you on the slide. The bottom, the denominator of the theorem is the evidence. And if you look closely at the evidence, it doesn't depend on the class that we are evaluating y sub c. So it's that value there is going to be exactly the same for all the considered classes. And therefore, we can remove that from our calculations and simplify the Bayes theorem by using just the numerator, which is the part that affects what we are going to predict. The probability of each of the classes is known as the prior probability. We can easily calculate that from the training data by the number of samples for each class divided by the total number of samples, so the proportion of samples for each class within the training sample. The other part of the equation is the conditional probability, which assumes that all the different independent features, all the different features are independent. If we assume that, then the conditional probability is the product of all the conditional probabilities for each feature. Now the question is, how do we model this conditional probability? Can we use a Gaussian distribution? Can we use a Bernoulli distribution or a multinomial distribution? We don't know. But we need to make a decision on how are we going to model this distribution. Say we decide to follow a Gaussian distribution. In that case, the only thing we need is the mean and standard deviations for each of these distributions. That is, for each feature and each class. Okay, because as I said, what we are interested in is the conditional probability conditional to each of the classes and for each of the features. Once we have these values, once we define the conditional probability based on the Gaussian distribution, and we have the mean and the standard deviation for each of these distributions, then we can calculate this conditional probability of a new sample, of an evaluated sample belonging to each of the class. So what are the variables involved in naive-based classifiers? In terms of hyperparameters, we need to know what are the conditional probabilities, the distributions, what are the distributions that are going to model these conditional probabilities. As I said earlier, is it going to be a Gaussian distribution? Is it going to be something else? In terms of the parameters, which is what we can compute, what we can automatically find out from the training data, what we need to, the parameters are the prior probability, as we saw earlier, and the parameters of the conditional probability, again, as we saw earlier. In the case of the Gaussian distribution, that would be the mean and the standard deviation, for example. So what are the advantages and the disadvantages of the naive-based classifier? Well, it's a very intuitive and straightforward concept because it's based on the Bayes theorem, and it's very fast at training and evaluation because we typically don't need to do many computations to obtain the parameters there and to evaluate a new sample. In terms of the disadvantages, The main disadvantage is that it assumes that the features are independent, and this is not typically the case in real data. So this will be the main disadvantage of naive-Bayes classifiers. Also, it requires prior knowledge of which is the conditional probability distribution of the features, of each of the features. And then it has the problem of zero probability, which is in the case of categorical variables, which are often encountered in mental health research. If we find a category that has not been contemplated in training or that we never encountered during training, then the naive-Bayes classifier is going to predict a probability of 0, which is not correct.